Good afternoon, all. Hope you're all healthy and safe. Let us continue with our module 1 and chapter 5, spectrum and Fredholm theory of compact operators. So in the previous lectures we had discussed about what is the spectrum of a operator, and in this lecture we are going to begin with the Fredholm theory of compact operators. Okay, so before going into the Fredholm theory, we are going to discuss a few lemmas and propositions and all. So let's move on to our first lemma of this section, lemma 5.2.1. Lemma is as follows: let E1 be a closed subspace of E, then there exists an element y dot in E whose norm is 1 and distance of y dot and E1 is greater than or equal to 1 by 2. So if we are given a closed subspace of the space E, then we can always find an element in the space E with norm 1 and whose distance with that closed subspace is always greater than or equal to 1 by 2. So let's see how we can prove this lemma. So first of all, we are given E1 is closed, right? E1 is closed subspace of E. Subspace of E. I'm going to choose an element y in E but not in E1. Okay, so y is an element of E but not an element of E1, such that distance of y and E1 is equal to some value greater than 0. Okay, that is, I'm choosing an element, choose y element of E by E1 or E bar E1, that is, it is an element of E such that distance of y and E1 is equal to A, which is strictly greater than 0. Now such an element can be chosen. Why? Because E1 is a closed subspace of E. So if I choose any element in E, I can find some element at E1 whose distance will be greater than 0. So keep this point in mind. Now let x dot be an element of E1, okay, such that this y minus x dot, norm of y minus x dot is less than 2a. Okay, so these are the assumptions. So keep all these assumptions in your mind. So I'm choosing another element x dot in E1 such that norm of y minus x dot is less than 2a. Okay, now we need to find an element in E1 whose norm is 1 and whose distance with E will be distance with E1 will be greater than or equal to 1 by 2, right? So what I am going to do is I am going to consider y dot equal to y minus x dot divided by norm of y minus x dot. Okay, all right, then what will be norm of y dot? Clearly norm of y dot will be 1, right? So one condition is satisfied. So I have got an element y dot whose norm is 1. Now I need to get the other condition, that is distance of y dot and E1 must be greater than or equal to 1 by 2. So for that I am going to choose an element in E1. Okay, choose an arbitrary element E1 and let us see what will be the value of y dot minus x, norm of y dot minus x. This is the distance, right? So what was y dot? Y dot was nothing but y minus x dot divided by norm of y minus x dot. So this will be, I am replacing y dot by y minus x dot by norm of y minus x dot minus x. Okay, so this is nothing but norm of y minus x dot minus x into norm of y minus x dot whole divided by norm of y minus x dot. So I can write this as norm of y minus x dot minus x into norm of y minus x dot by norm of y minus x dot. Okay, so here just look at this. X dot was an element which was chosen from our E1, right? And x is also an element of E1. X is also an element of E1, and so E1 is a subspace, so this implies norm of y minus x dot, that is a constant or a scalar value, into x is also an element of E1, and they are linear combination. That is, if I am grouping it like this. Okay, let me write it again. We'll have norm of y dot minus x can be written as norm of y minus, I'm grouping the terms of E1 together, plus x into norm y minus x dot. Okay, so this whole term is an element of E1, whole divided by norm y minus x dot. Now we had two assumptions. One was distance of y and E1 is equal to a, and the other one was we had chosen x dot such that norm y minus x dot is less than 2a. Okay, so I'm going to use these two equations here. So if norm of y minus x dot is less than 2a, this implies what will be 1 by norm of y minus x dot. 1 by norm of y minus x dot will be greater than 1 by 2a, and this value norm will be equal to a. So I am substituting this here, so I will get the numerator is a and the denominator is greater than or equal to 2a. So it is a by 2a, which is equal to 1 by 2. So therefore I can obtain norm of y dot minus x, okay, will be greater than or equal to 1 by 2. So y dot was the element of E whose norm was 1, and its distance with an element of E1 is always greater than or equal to 1 by 2. So x was an arbitrary element, so I obtained an element y dot in E such that norm of y dot was equal to 1 and the distance of y dot and E1 is greater than or equal to 1 by 2. So this was our lemma 5.2.1. We'll be frequently using this lemma to prove other various other propositions and corollary and all. So just go through the lemma once again. Let E1 be a closed subspace of the space E. Then we can always find an element in the space E whose norm is 1 and whose distance with the closed subspace is greater than or equal to 1 by 2. So that was lemma 5.2.1. Now we have a corollary of this lemma, corollary 5.2.2. That is, if the dimension of the space X is infinitive. So if you are considering an infinite dimensional space, then the identity operator will not be compact. Okay, so this is a simple proof which we are going to prove with the help of the previous lemma. So what we have to prove is, we are given a space X, okay, whose dimension is infinity. Okay, dimension of X is infinity. Then we need to prove that the operator, identity operator I from X to X is not compact. That is, if I take any element or any subspace, any sequence, then it will not have a corresponding Cauchy's subsequence. Now as we are considering the identity operator, so if I take I of x, that is actually x itself, so you have to consider, you don't have much complication in that. So what I'm going to do is I'm going to consider the family of subspaces, consider the family of subspaces of x such that E1 is a subspace of E2, etc. It is a subspace of En, okay, where I'm choosing subspaces such that their dimension is finite. Okay, I'm choosing subspaces of x whose dimension are finite. Now we have a result in linear algebra and all, that is finite dimensional subspaces will be always be closed. Okay, I'm not going to go for the proof of it, you can just verify it. The finite dimensional subspaces will be closed. So as EI's are finite dimensional, they are closed. Okay, so once we have a closed subspace, what can we use? We can use the previous lemma. So by lemma 5.2.1, there exists yi element of EI with norm 1. Okay, lemma we had stated just about a single subspace. Here we are considering many subspaces, such that the distance of this yi and previous subspace EI minus 1, okay, will be greater than equal to 1 by 2. That was how we had done the previous lemma, right? We had obtained an element y dot such that norm of y dot was 1 and distance of y dot comma E1. Okay, so if we are having yi, then the E will be the next one or the previous one. So distance of yi into EI minus 1 is greater than or equal to 1 by 2. Okay, so if this is true, that means I and I minus 1, right? So since we are dealing with closed subspaces of the given space, norm of yi minus yj, okay, will be greater than equal to 1 by 2, right? Distance of yi and ei minus 1 is greater than equal to 1 by 2, where I is not equal to j. So here clearly I and I minus 1 are not same. So yi minus yj, where I and j are not equal, the norm or the distance will always be greater than equal to 1 by 2. So I can say that this is not Cauchy's, right? This sequence yi is not Cauchy's. So if this is not Cauchy's, it cannot have a Cauchy subsequence. So yi was an arbitrary sequence chosen, is not Cauchy's, so it cannot have a Cauchy subsequence. So the space or the linear operator I will definitely be not compact. Okay, yi is not Cauchy's means I of yi is yi itself, so that is also not Cauchy's, right? So with the help of the previous lemma, we could easily prove that this space, that is the identity operator, okay, the identity operator is clearly not compact. Okay, so I hope you have understood how we have proved this with the help of previous lemma. Now we shall be discussing just one more proposition, that is also a simple one line proof which uses the previous corollary. So this is linked. First we proved the lemma, then we proved a corollary with the help of the lemma. Now we are going to prove a proposition with the help of the previous corollary. So proposition 5.2.3 is, for every compact operator, 0 is an element of sigma of t. Okay, that is 0 is a part of the spectrum of that particular operator. If the operator is compact, then definitely 0 will be the spectrum point. So how can we do that? So for that we are going to use the method of contradiction. That is, first of all I am going to assume that 0 does not belong to sigma of t. Okay, if 0 does not belong to sigma of t, then t minus 0I inverse exists, right? That is the definition of regular point. It is not a spectrum point, so it has to be a, if it is not a spectrum point, then it has to be a regular point. So t minus 0I inverse exists. So what is t minus 0I inverse? That is nothing but t inverse, right? So t inverse exists. So such an operator exists. Now we'll be using the proposition 4.3.4. So just go through it. 4.3.4, third part. Okay, that is in this proposition we had proved that the compact operators, the collection of compact operators forms an ideal. Okay, compact operators forms an ideal. Now we all know what is the definition of ideal, right? So here we are given a compact operator T. Okay, so given T is compact and T inverse also exists. So by the property of an ideal, T into T inverse must be compact, right? Because set of compact operators forms an ideal. So T into T inverse is just an operator and T is a compact operator, so their product must be compact, right? So what is T into T inverse? It is nothing but the identity operator. So identity operator must be compact. So this forms a contradiction to our previous corollary, right? That is, if the space is infinite dimensional, then the corresponding identity operator is not compact. So if we had assumed that 0 is not an element of sigma of t, we will get that T inverse exists, and in turn we will get that I must be compact. But that is a contradiction. So therefore, what can we conclude? We can conclude that 0 is a spectrum point if T is a compact operator. Okay, so this is what the last proposition states. Last in the sense, last proposition of this section, that is proposition 5.2.3. So we had stated a lemma, and by that lemma, with the help of that lemma, we could prove this proposition. That is, for every compact operator, the corresponding element 0 is an element of the spectrum, or 0 forms a spectrum point. So that's it for today's session. Thank you.